Hello students, this lecture is about common misinterpretations in statistics. Once you understand all the concepts related to statistics, this lecture will additionally help you to clarify the doubts related to statistics. Scenario 1. Monthly rainfall is associated with the incidence of leptospirosis. Total rainfall during the last month was 60 millimeters, standard deviation was 10 millimeters. We know that when we are getting more and more rainfall, the incidence of leptospirosis increases. This is related to that. This question is related to measures of central tendency and dispersion. The question is whether using mean to summarize the variable rainfall is appropriate in this scenario. Some of the students are in an understanding that the continuous variables always follow a normal distribution. All continuous variables do not follow a normal distribution. Naturally occurring biological variables without an external influence tend to follow a normal distribution, but that is not a universal phenomenon. Because of that, this statement is false. Rainfall, harvest, and many other continuous variables do not follow the normal distribution. Therefore, it's better to use median and interquartile range to summarize rainfall data. Scenario 2. A researcher is planning to determine the average height of adult patients with trisomy 21 or Down syndrome. One of the four special care centers situated in close proximity is to be selected. Following are the number of Down patients in each center. Now, in this study, we are going to select one center as our study setting and we are going to recruit all patients within the center as our study sample. Center 1 includes 15 patients, Center 2 includes 25 patients, Center 3 includes 35 patients, and Center 4 includes 50 patients. Now we are going to select one out of them. The question is which of the sample will be the most dispersed distribution? When we are talking about the dispersion, it's important to consider the standard deviation. As shown in the diagram, if the standard deviation high, it will be a more dispersed distribution. If the standard deviation is low, the distribution will be a narrow distribution. Look at the standard deviation formula. Standard deviation is inversely proportionate to n minus 1. Because of that, somebody might come into a wrong conclusion that when we are increasing the sample size, standard deviation might decrease. But standard deviation is also proportionate to x minus x bar, which is in the numerator of this formula. When we are increasing the sample size, n minus 1 will go up. In the meantime, there will be additional x minus x bar items included into the formula. Because of that, standard deviation will not be changed with increasing the sample size. However, it's false to conclude that standard deviation will not be changed with increasing sample size. The reason for this is the probability of capturing the outliers is increased with the increasing sample size. When we are increasing the sample will be more close to the population. So the probability of including outliers into the sample is increased. So we expect a slight increment of standard deviation with increasing the sample size. So the answer is the center with 50 down patients because the highest sample size will get the highest standard deviation. Scenario 3. A researcher hypothesizes that the average weight of rugby players is higher than the average weight of cricket players. The alternative hypothesis of this research is mean weight of rugby players is significantly higher than the mean weight of cricket players. So, what is the null hypothesis? Many students state that the null hypothesis as mean weight of the cricket players is significantly higher than mean weight of rugby players, which is not. We need to understand clearly that the null hypothesis is not the opposite of alternative hypothesis but the negative form. We need to state that mean weight of rugby players is not significantly higher than mean weight of cricket players. This is one of the common mistake and misconception in statistics. Scenario 4. A researcher hypothesizes that there is a significant difference of the systolic blood pressure between patients with type 1 diabetes and type 2 diabetes. So the correct null hypothesis is there is no statistical significant difference between the systolic blood pressure between patients with type 1 and type 2 diabetes mellitus. These are the results of this study. Systolic blood pressure difference between the two groups is 10 mercury millimeters. The p-value is more than 0.05. Based on these results and assuming that the predetermined cutoff value for the p-value is 0.05, we can conclude that the null hypothesis is accepted. However, this conclusion is conceptually false because from the beginning of the study we state that the null hypothesis is true. That means from the beginning of this hypothesis testing we assume that the systolic blood pressure of type 2 diabetes population and the systolic blood pressure of type 1 diabetes population are equal. And considering this, we try to identify the probability of observing this observed difference of systolic blood pressure. Although we assume that the average blood pressure of two populations are equal, when we are obtaining samples from those populations, there can be slight differences. We call that as sampling variation. Now, the question is whether this observed 10 mercury millimeter difference is purely due to sampling variation or due to the difference of the type of diabetes. What is the probability of observing 10 mercury millimeter difference due to sampling variation? Is it high? If it is high, there may not be pure difference between the systolic blood pressure between the two types of diabetes. But if the probability of observing 10 mercury millimeters due to sampling variation is less, this difference could be due to the differences of the type of diabetes. I explained the basis of hypothesis testing as we are assuming that the null hypothesis is true from the beginning of the study. It's better to state that there's no adequate evidence to reject the null hypothesis rather than just stating that the null hypothesis is accepted. Scenario 5. A principal of a school estimated that the probability of passing the GCE advanced level examination in the school is 50%. Many students who have less understanding about the statistical concepts or who are confused with statistics state that the p-value is zero point 0.5, which is strong. You need to carefully understand the concept of p-value. Scenario 6. A new cancer drug is tested against the existing drug. The p-value for the test is zero point 0.04. As the p-value is zero point 0.04, somebody might conclude that as the p-value is less than 0.05, because of that it's significant. Or else somebody might consider that p-value of 0.05 is a universal phenomenon. But it's not. We always need to compare the current p-value against the predetermined cutoff value. Predetermined cutoff value has to be decided by the researcher or research panel or by an expert panel. We need to carefully consider that p-value of 0.05 is not a universal phenomenon. This is one of the common mistakes that the researchers do in their research. If the predetermined cutoff p-value is 0.05, it is obvious that the p-value of 0.049 is significant. But what about this? Are we going to say that the p-value of 0.051 is not significant? Generally, we consider that also as significant. However, as the predetermined cutoff value has set to 0.05, we need to carefully look into these close non-significant p-values. The researcher or the expert panel has to decide this slight difference of probability value can be considered as non-significant. If the research has done with a low sample size, definitely this 0.051 is going to be a significant result. Scenario 7. Average hemoglobin level of a sample of 100 antenatal mothers is 10 grams per deciliter. Standard deviation is 2 grams per deciliter. Calculate the standard error of mean or SEM. Standard error of mean equals standard deviation divided by the square root of n. What is this standard deviation? Is it sample standard deviation or population standard deviation? This is population standard deviation. However, if we have obtained a random and representative sample with adequate size, standard deviation is more or less equal to the population standard deviation. Because of that, in practical situation, we use the sample standard deviation if we don't know the population standard deviation. Because of that, we need to state the statement as standard error of mean equals sigma divided by n root or the population standard deviation divided by the square root of n. Scenario 8. Average hemoglobin level of a sample of 20 antenatal mothers from village A is 10.2. Standard deviation is 2.2. Average hemoglobin level of a sample of 20 antenatal mothers from village B is 10.5. Standard deviation is 2.1. Which of the following table should be used for this scenario? Whether it is Z table or is T table. I use green color cross for this because there was an accepted thing. If the sample size is less than 30, we use T table, and if the sample size is more than 30, we use Z table. However, the probability values of the Z table or Z distribution are when the sample size is infinity. If the sample size is less than infinity, we have to use the t distribution. There are infinite number of t distributions for different sample sizes, and we need to carefully understand that the probability values of the z distribution is slightly different from the t distributions, even though the sample size is high. In the era where the computer softwares were not available, people used Z distribution, but now we don't have to use Z distribution because we can we can get the probability values of T distribution despite the sample size. Scenario 9. An oncologist claimed that the clinical effectivity of the new cancer drug is same as the old cancer drug. However, a study conducted revealed that the new drug is better with a p-value of 0.05. The study was conducted using a lower sample size. There were no sampling errors. Can we get a non-significant result by increasing the sample size? In this example, the oncologist or the treating physician experienced that the new drug is almost same as the old drug. However, the study revealed that the new drug is better. Still, there's no clinical effectivity. Now, the other thing is they claim that the study was conducted using a lower sample size. Many researchers think that we can get this expected non-significant result by increasing the sample size. But here it's clear that there were no sampling errors. So what will happen is when you increase the sample size, this significant level will be increased. What has happened here is type 1 error in statistics. Even though the clinician does not feel any effectivity compared to previous drug, statistics says that it's effective. When you increase the sample size, the sampling distribution or the null distribution get more narrower and there's high power to get a significant result. Because of that, you cannot eliminate type 1 error by increasing the sample size. You can only eliminate type 2 error by increasing the sample size. Most probable thing that could be happen in this scenario is predetermined cutoff value was not adequate. The predetermined cutoff value here was 0.05 and our result was 0.04. If the researcher has decided zero point zero 0.05 cutoff level may not be adequate as this is a cancer research, we need to go for 0.01. If he has decided like that, this problem will not be there. Then the zero point zero 0.04 result will come as non-significant. The learning point here is we cannot eliminate type 1 error by increasing the sample size. We need to adjust the significant level according to the scenario based on the experiment. Scenario 10.1. Displayed is a result of AST values of alcoholic group 1 and non-alcoholic group 2 individuals. Comment on the statistical significance without testing. Question here is whether we can talk about the significance level without doing a statistical test. Look here carefully. The lowest AST level of alcoholic group is more than the highest AST level of the non-alcoholic group. There's a clear difference and there's no overlap at all. In this kind of situation, if you have a good understanding statistic, you need to understand that anyway this is going to be significant at any level of significant or any level of predetermined cutoff value. So, it is false to conclude that we cannot comment on statistical significance without performing a statistical test. We can always have some idea about the statistical significance by visualizing the data. Scenario 10.2. Does this show a clinical significance? This is the most important question in statistical learning. We are not talking about clinical significance, we are only talking about statistical significance. If something is statistically significant, in order to say that there's a clinical significance, there are so many other criteria to be fulfilled. The things like Bradford Hills criteria are some of the examples for that. Scenario 10.3. Does this mean the samples are statistically significantly different? Somebody might think that yes, there's a statistically significant difference, but the conclusions are not regarding the samples. Always, our statistical conclusions are regarding the populations. So, does this mean the samples? No, these are regarding the populations. This is a true false type MCQ from today's lecture. Which of the following statements is true with regard to statistical significance? If the predetermined cutoff p-value is 0.05. A p-value of 0.02 indicates that the result is likely to be due to chance. P-value of 0.02 means the probability of occurring this by chance is only 2%. So it is less likely to be due to chance or less likely to be due to sampling error. Because of that, this statement is false. STEM 2. A p-value more than 0.05 could be due to type 2 error which can be minimized by increasing sample size. When we get a non-significant p-value which is closer to the predetermined cutoff value, we always need to cross-match with our sample size with the predetermined sample size. These non-significant results could be due to type 2 error, which can be minimized by increasing the sample size. Because of that, this statement is true. Stem C. Null hypothesis is accepted if the difference between two groups is not statistically significant. As I explained with the scenarios, we can conclude that the null hypothesis is accepted when there's no significant difference between the two groups. It's in a way it's true, but we don't state it as null hypothesis is accepted. We have to state this as no evidence to reject the null hypothesis. I explained this with the one of the scenario. Please go and refer for further details. Because of that, this statement is false. Stem D. A p-value of 0.03 indicates that the result is less likely to be due to chance than a p-value of 0.02. Now we need to carefully look into these two p-values. Both are significant at the predetermined cutoff value of 0.05, so it's less likely to be due to chance. Here 0.03 indicates that there's 3% probability to occur this by chance. 0.02 means there's 2% chance to occur this by chance or the sampling error. Because of that, 0.02 is less likely to be due to chance or more significant. Because of that, the stem is false. Stem E. In a study assessing the effectiveness of a drug, a p-value of 0.0001 indicates clinical significance. 0.0001 indicates statistical significance but not the clinical significance, as I explained in the last scenario. Thank you very much. I hope you understood some of the misconceptions regarding statistical interpretations. I hope to meet you in another lecture. Thank you very much.